Alright, thanks everybody for coming. My name is Alex. I see a lot of faces I don't know, so this means you also don't know me probably. So I used to be one of the guys who started this meetup here. Then I kind of disappeared for a while. Here I'm back. So with a talk about a tour of GHC 8.0, and I'm excited to show you what we got, what new stuff is there. So first of all, unusually enough, I'll start with an inverse agenda. I'll show you stuff I will not cover in this talk, because the list of features is actually huge. And if I go into all depth, this will take us hours, so we don't want to do this. Still, I want to give you an overview so that you heard about it at least. Okay, type system stuff. This is all towards dependent types in Haskell. This topic is non-trivial, highly non-trivial in its own, and I think it deserves its own talk anyway. So I'll only go briefly over what features are there. So there's a new flag, you can say undecidable superclasses. So in case your superclasses are recursive, usually the type checker rejects it. And with this you can say, okay, chill, I checked it for you, it's gonna be fine, hopefully. Similar to undecidable instances, basically. You can have visible type applications, so that's pretty neat if you have polymorphic types. You can have add, you can say add and then pass in the type, and this will force the type of the polymorphic function to be what you tell it to be. This is sometimes necessary if you don't have an argument. You could pass a value, you could pass to have the type inferred. Type family dependencies is something like functional dependencies, but for type families. So you can basically let the compiler know that this type family is injective. So more stuff is, this is less ambiguous and more things can be allowed. Type in type, this feature, like this flag, enables a whole set of features. It's an extension to the polykines. I have a typo here, so this is polykines, which was the first step to have polymorphism on kind level. So it's really all about type level programming here. And type in type is just the next step, and it's highly experimental. You shouldn't use it unless you know how to debug the compiler itself. So there's support to reason about kind equalities. You have wildcards in data and type family instances. Basically all the things you need to kind of do functional programming on the type level itself, right? That's what dependent types is all about. At least in my limited understanding, I have to say. And the nice thing is a little bit magic. You can derive, instantiate a special class, and then somehow you can control what type errors the compiler will report in case something goes wrong with your own types. So that's, as I said, we needed a separate talk for this. If nobody from you wants to do this, maybe I can tackle it at some point, but this needs good preparation. Let's move forward. Template Haskell. So a lot of stuff, good stuff there as well. I'll not be able to cover in this talk. So template Haskell quotes is basically a safe subset of template Haskell. So template Haskell allows you to quote things and to splice them. So quote means move from the concrete Haskell syntax into the AST representation in a data type that you have available in template Haskell that gives you the information about the values and the types. Now splicing is the way back. So you constructed something in template Haskell, now you want this value in the code. Now splicing is unsafe because template Haskell has I/O available, so you can do whatever you want. So if you can splice that value, the whole program is then unsafe. I'm talking about the safe Haskell extension, if you heard about it. You can mark modules as being safe, and there's no danger from executing any code from those modules. So that's nice. So we can have at least some template Haskell without sacrificing safety for the module. Then the lift type class. I must say the term lift is highly overused. So this time we talk about taking a value and representing it as a template Haskell expression in the Q monad. So you can automatically derive instances. That's nice. You now have access in template Haskell about the enabled language extensions, so you can make choices depending on that. You have support for typed holds, if you heard about those. So if you say somewhere, if you don't know the type of something, you just say underscore something, and then let the compiler run over it. It will say, well, I found this type hold, and I think it should be this type. This helps a lot sometimes to solve type puzzles. And this is also available in template Haskell now, which is pretty nice. And you have information about strictness and unpacking annotations for data types. So you can also depend your generated code on that. Pattern synonyms is a own set of features I don't know much about. So basically you can, if you have a pattern, it's complicated, you can provide a synonym for it, so you don't have to repeat the pattern all over again. So now you can export pattern synonyms from modules, which is new, and there's some record syntax for patterns now also available. A huge, like a whole set of features around warnings. First of all, if you've worked with complicated patterns, for instance guards, or if you have a generalized algebraic data type, sometimes the compiler just doesn't get it that actually your patterns are exhaustive or they're not. Usually he doesn't get that they are exhaustive, so he's going to warn you about non-exhaustive patterns. So you have to put a wildcard or catch-all pattern, which kind of forfeits the purpose of the check in itself, because now you're not like future-proof against extensions. Like the compiler won't tell you there's a new pattern you might want to cover. So there's a huge improvement on that. Oh, and I didn't mention, like most of them, there's always a paper behind it, right? So you want to know the details, just go and read the papers. That's pretty nice. You can have the compiler issue warnings about unrecognized warning flags. I'm not sure who needs this, but anyway. I guess sometimes if you move forward and old warnings are removed, you might want to know that. There's more symmetry now. There's a double W no XXX something warning, which is basically the same as the F no warning flag. What is pretty nice, if a warning is issued, the compiler will tell you with which flag you could disable this warning. That's pretty neat. And it will give you more insights about when it failed to specialize things. It will give you issue warnings about this, so you get more insights into what the compiler is actually trying to do. All right, and last but not least, also I'm not going to cover this, right? There's more stuff I'm going to cover. Instrumentation for tracking of compiler performance. This is about Fusion. It's really hard to know whether the Fusion succeeded or not. And Fusion is about if you have a list and then you apply the first function and then the next one and the next one. You could apply, you don't have to instantiate the intermediate lists, you can apply one combined function immediately. This is called Fusion, it's a huge performance saver. But it's not so obvious when the Fusion optimization kicks in and when it doesn't. It's really tricky. So people have been very creative how to get information about this. You don't always want to read the core, the compiled core to understand this. So now you have instrumentation for that, so the compiler will tell you. You have improved dwarf support. I don't know if you know dwarf, if you do C programming or something. So it's a debugging format. It's pretty awesome. It supports like a multitude of languages. GDB supports it. It's pretty neat. So now you have dwarf support. Basically, this means you can run GDB on your Haskell binaries and get some more interesting stuff out. And ARM, the ARM backend is like much better now. I don't know much about this, but anyway. So just for completeness. Okay, this is all the stuff I'm gonna not cover. So now let's dig into things I want to cover. In my opinion, these are the really interesting, not saying the rest is not interesting, but real big deals here, except for the type system features. Alright, let's do this. MonadFail. Okay. So let's look at the evolution of the class monad. So this is how you know it, right? You have a return, you have a bind, and you have this ugly fail. And nobody really knows when you need it or not, but it's supposed to be there, so whatever, right? So I'm going to shed some light into this today. So this is how it used to be, and then with 7.10 there was the applicative monad proposal, where people were saying, well, mathematically every monad is an applicative, but we can't express this in the type system, that's a problem, so we need to change that, and they did. So, and I really want to say this is great that the Haskell community is willing to risk breaking changes, otherwise you're going to end up in the C++ destiny of endless backwards compatibility and language complexity. So this is really great that they took enough of willingness to do this. So, okay, now every monad is an applicative, which means you can have a default implementation. Return and pure are really just the same thing now. And okay, but fail is still there. This is still ugly. So next step is to get rid of that. So now with the MonadFail proposal, we have another class which is called MonadFail. Every monad can be a MonadFail if you tell me how to fail. And the standard monad has no fail anymore. Okay, why is this important? What's the big deal here, right? Okay, let's look at this example. So we have some data type, called D with two data constructors A and B. We have a function that is abstract over the monad it runs on. So you don't know which one it is. It's some monad, that's okay. You have a function G that returns a value of type D, you pattern match on it, and you move forward. Well, what's the problem here? Well, what if the pattern doesn't match, right? G could return a B, okay? So now let's look at how this is desugared. So this is a core, no, excuse me, this is not true. This is after, directly after desugaring. So how is this piece of code desugared, okay? So actually what is happening, you call j of x, you call the bind operator, and now you create a new function with some fresh variable, and it does a pattern matching on what you just, the value you gave it. If the pattern matches, it moves forward with the rest of the code, otherwise it calls fail. And fail is a function from the monad instance, okay? So if G returns a B instead of an A, then the function f will fail, okay? So why is this not good enough? So let's look at how to implement fail. So for some monads it's simple. So maybe you can just, return nothing. That's really the right thing to do here, right? You failed, so, okay, you return nothing. But how do you, excuse me, and if you run this program I just showed you, actually it will return nothing. Fair enough. But how do you implement fail for either? So you get a string, and now what? Right? You're supposed to return, so if you look back at the type, you're supposed to return some A, any A, whatever, but you're supposed to stop computation. So computation in the either monad stops with a left value, but you don't know what left is. It's some abstract E, so you can't instantiate it. So there's no way to implement fail for either of E. So the only thing you can do is throw an error, like a runtime error. Okay? So if we run this program, we indeed get a runtime error. Okay? And this is really a problem because the function f is sometimes total, sometimes not, depending on which m you use, and the type doesn't tell you that, right? And this is really terrible. So this is what this fixes. So by removing fail from monad and requiring a separate class, we can now say, okay, so f really needs a monad fail, right? And if you enable this feature with monad fail desugaring, the compiler will tell you, wait, you have a pattern here that might not match. I really require monad fail here from you. If you don't provide me one, I'm not going to compile it. Desugared this time looks pretty much the same, only this time the function fail is the one from the other class. So you can still run the program for maybe, but for either, if you try to run it for either, it will tell you there's no instance for monad fail for either. So we turn the runtime error into a compile time error. And if there's one thing we love here, it's compile time errors, right? So well done. So that's what it's about, monad fail. And I would really, really recommend everybody to enable this feature. Okay, questions so far? Actually, at any time, just interrupt me, ask stuff. Yeah, go ahead.
Enable this feature, is it optional then? So the monad fail, is it optional in GHC 8?
So if you, so you have to enable with this monad fail desugaring flag.
Oh, okay, so if you actually use monad fail, the class, then you...
So if you don't enable this flag, then the compiler will not force you to use monad fail type class.
Ah, okay, so then
it's the old behavior.
There is no breaking change.
That's the old, yeah.
Ah, okay, I see.
Is there a set of standard classes for which it's already implemented by this proposal?
Yeah, I mean, yeah, yes. Okay, good. Next topic, ApplicativeDo. All right, so we asked GHCI, what's the type of this funny little thing here? So it has a do, so it must be something monadic, and indeed, it tells you, well, it's a function that takes an m of bool and returns an m of bool. Okay, but now we enable the new flag and ask him again, and he tells us, well, this time it's a function from f of bool to f of bool, where f is a functor. What? So, okay, the do syntax gets desugared to functor. If we use multiple values, then functor doesn't cut it anymore because functor is not powerful enough. This time it tells us, well, okay, you need applicative to run this. But that's actually enough. You still don't need monad. And only when you have data dependencies, well then okay, then you really need monads. Right? That's a big deal between like applicatives and monads. If you can have data dependencies and monads. This time it tells you, okay, so we need monads. So it's really about reducing the actual required feature set if you desugar a do block, right? So let's look at the core, like the GHC core of how exactly this looks like. So we have this function, takes an M, it unwraps it from the monad and returns the negated version of it. Okay. So if you dump core with ddump simple, so we have to check this really a little bit careful. So the first argument, the thing with the add, is the type. That's right. So and the second one, the thing with the $D, that's a dictionary for functor, right? And now M finally is M, the one that we know. And indeed, if you look at the code, it uses fmap from functor. Okay, that's pretty neat. So it's actually this function, right? If you manually desugar, this would be the same. And you actually, what I show you here, compiles to the same core code than the one with do notation. When you try to desugar applicative, so how does this actually desugar, right? So how is applicative enough to support this code? Oh geez, okay, let's look at this. Okay, another type application, fine, another dictionary, fine. Etta is our M, for some reason the desugar decided to call it etta. Okay, so we have the funny little applicative function here, and we have an fmap inside. Okay, I took the time to desugar this for you. This is what this results into. So what do we do here? So the dollar in braces is the fmap, and the other one is the applicative. So on the left is a pure function. With fmap we lift it into the applicative, and we say, okay, give me the x, give me the y, I'll do x or y for you. And both x and y are applicative, like wrapped up values, the m of character A and the m of character B. Right? Is it for you obvious that the bottommost and the topmost code is exactly the same? So it turns out, yeah, actually, you don't need monads to, for this kind of do blocks, because there's no data dependency, right? Okay, now finally we desugar monad and we look at it, and so we have again a type argument, again the dictionary. The let block is just to climb up the chain of superclasses, because the monad is an applicative, so the dictionary contains the other dictionary. So this is unwrapping the dictionaries basically. And then it's the bind, and within the bind we see an fmap. So what is actually happening here? So this is how he desugars it. He goes like, well, I only need the bind for the data dependency. The rest I can still cover with a functor. So it goes really minimalistic as much as possible. Is it obvious to you that the two codes are the same? It was not obvious for me for a long time, I can tell you. So okay, good. So why is this important? Why do we care? Why is it so important? I mean, for all we care, like monad applicative, who cares as long as it works, right? And indeed, in most of the cases, the applicative function and app, which is a function from the monad library, are actually the same in most of the cases. And you can implement app, which has exactly the signature of the applicative function, using bind, right? You unwrap the function, you unwrap the value, you apply the function, you wrap it up, right? So this is really what you do in like most of the cases. And indeed, the default implementation for the applicative function can be app, now that applicative is actually a superclass of monad, right? And this is what's in the library, the standard library. But sometimes this is not the case. Sometimes you do not want app to be the same as the applicative function. And why is that? Let me give you an example. So this is from the Haskell paper, and the whole motivation behind this is the Haskell project, like Simon Nolo's Haskell-based project at Facebook, where they do like really interesting stuff regarding implicit concurrency. So let me show you. So there's a data type called fetch. It has two data constructors called done, and the other is called blocked. And the block contains a fetch. Now this is a pattern that you see a lot. Basically, you can move up to some point, and then you have to do something else before you can move forward. And it's actually, the structure is a free monad if you know about this. So anyway, okay, so we can have an instance of functor that's pretty straightforward. So you unwrap the value, you take the function, you apply to it. Okay, that's it. It's pretty simple. Applicative. So you look at the left side, you look at the right side. If one of them is blocked, the result must be blocked. But the key here is the highlighted line. If both are blocked, you only need to preserve one of the blocks. This is in contrast to the monad instance, where you always preserve the block of the outermost block. So because in a monad you get a wrap value, and then a function that takes a plain value and returns you a new wrap value, you don't have two wrap values at hand at the same time because of this data dependency. So you have to go one after the other. That's the whole point about the data dependency, right? That's one after the other. So now if we write a small example program where example applicative and example monadic are exactly the same functions, except for the one uses app, the other one uses the applicative function, and we print what we receive, then in the applicative case we only have one block, and the other one we have two levels of block. Okay? Okay, still, why is this important? To understand the whole thing, you really need to read the paper, but the point is, the execution environment that they have, for each block they will actually do an I/O action, reach out to some backend servers, go get the data, bring it back in. So this is really that the computation has to stop and you do some extra effort. So with every level of removed effort, you speed up the whole thing. Right? So it was really important that they don't use monads, which force serialization basically line by line. With every semicolon, with every bind, you force the serialization. While with applicative, you can express a whole lot of things in one row, if you will, and then they're executed at once. But they still wanted some nice syntax for it, and that's where the whole ApplicativeDo came from. Let's look a little bit closer. So if you have this now, so what's the big difference here? I don't say explicitly return, right? I just say m. And m obviously is a function that will wrap it up. Okay? So how can we desugar this? It looks like applicative is enough to desugar it, but not quite. If you look at the core again, and let me translate it for you, you see the right part is the same, but there's an outermost join. So what is join? Join is a function from the monad, which belongs to monads, and it's actually the one that makes monads strictly more powerful than applicatives. If you have a wrap value that is wrapped, you can remove one level of wrapping. So m of a to m of a. That's what join does. And that's the one thing applicatives cannot do. Right? So mathematically, this is the big difference between monads and applicatives. So in order to desugar code like this, you still need some monadish stuff, right? But if you look at how you can implement join, well, join can be smart and again remove, like if you have blocked of blocked, it removes one of the blocks. So you can still have the performance benefits, right? Another tricky corner case. So if you look at this, so there are some things that are depend on each other. So the computation C requires the result of the computation A, but the rest is kind of independent. We don't look at core, it's really terrible. But I did the work for you and manually desugared it. So this is what we have. OMG, this is still pretty complicated. So what is going on here? If you look at the right side of the applicative function, the D and the B, this is the stuff that runs in parallel. And the one that is inside the join, that's the stuff that runs sequentially. So one notation, if you allow me a pseudocode notation, if you say a pipe is parallel execution, and a semicolon is sequential execution. So this is how it's going to execute it. So it's going to execute A and B in parallel, then wait for the result, execute C, and while this is happening, we can run D, because D doesn't care about the rest. But this is actually not the only way to run this. You can also run it like this. So we can also first run A, wait for the result, right? And then run B and C in parallel, and D again can run in parallel, do its thing. So which one is it? Well, one of them. It's not specified, just one of them. The only thing it guarantees that the order is preserved, so the semantics is preserved, and you don't have to care much. I still find this interesting because the whole ApplicativeDo feature adds a lot of complexity, let me put it like that. But I understand the benefits as well. So, okay.
In this case, you can actually do better if you move the. It actually makes a real difference if you move the x2 below the x3, right? Because then you get more parallel execution, if I see that right.
So, depending on the effect, so the question was, can you move x2 below x3? You as a programmer can, if you think you understand the effects. The compiler cannot.
Right.
Because the applicative might be sensitive to the order of execution.
Right, well, what I mean is that if you just thought of the feature as with ApplicativeDo, it will magically figure out all things that can be parallelized, right? It's not actually the case, because here you as a human could say, it doesn't depend, right? So
yes.
It doesn't matter which order I do it, but actually it does matter because it's like a bracketing operation, right? The fact that the x2 is between the x3, which uses x1, and x1 forces it to be executed before
yes.
x3, right?
Yes, it's like a barrier or something.
Yeah, so you still have to be smart if you want to have like maximal parallelism.
Absolutely, this is true. Yes. Yeah, and the compiler can't figure this out for you, right? All right. Good. Questions so far? Am I too fast? I guess I'm not too slow, so.
I actually found it interesting that they chose in the end to use this automatic, let's say, using do itself, right, and figure everything out by this kind of like data flow analysis, versus the approach of just saying like a do or something like this that forces the whole thing to be applicative, for example. Because one thing that I find problematic is that if you have one type that's an instance of both, but one of them has like nicer parallel semantics. Let's say you have like a build system, right? And if you use just MonadDo notation, then you can say, build me first this thing, then build me the other thing, do something with it. Then one problem that I find a little bit with this is that I cannot really, from the context, say the entire block is allowed to be applicative only, because in some cases I want to do that, right? I want, for example, to say that the thing is not powerful enough to do like monadic actions in between. And now I cannot easily do that, right? Because I cannot say I want this do block to be applicative only. Because if I annotate it with, let's say, : just that monad, then it's fine. It's still fine because both instances are the actual type, right? So I was wondering if I want to declare, I want to write a do block now that is only allowed, let's say for my own sake, right? Of course, if I type went through it manually, I could tell it by myself, but let's say I have this really long block and I want to make sure that I only use applicative operations.
I think the answer is, as usually, new types.
Right.
So introduce a new type that is not a monad, but is an applicative, and then you wrap it and unwrap it.
Yes. Yeah, that's the one thing that I found like a little bit uncomfortable about this. I would have found it the nicest if, in addition, they gave me a tool so that I can just force this with a very simple deliberation.
So there's also the other thing, right? If you look back at this example, sometimes, although everything is in parallel, you still need the power of join, which is not applicative, right?
Yeah.
And in general, I must say, so after reviewing all the stuff they've been doing, the Haskell community really, really strives for generalization. They hate introducing new stuff. They love taking the existing stuff and making it more powerful, more generalized. You see this all over the place. And I guess that's one of the reasons why you don't want a do, like ApplicativeDo, but try to solve it with what you have.
The thing is just, the main danger I see is just that you accidentally introduce one operation that needs the monad power, and then the entire thing gets its parallelism turned down.
Yes. I guess new type wrappers are really your friends here if you really care. Okay, next feature, also really nice stuff. It didn't quite make it right? So it's only half of it is in there, but it's still interesting what you have. So let's show it. Let me show it to you. Duplicate record fields. Finally, you don't have to do these weird prefixes for each record, because now they won't collide anymore, right? You can have data types in the same namespace that use the same record names. And all I can say, it's really not a problem, because the type system is smart enough to every time it's unambiguous, it will just pick the right one. If it's not unambiguous, it will tell you, right? So if I say MKA, I can create an A and just use the field name. That's fine. I can update the A and just use the field name. It's fine. I can select a value out of the A. That's fine, because every time from the context it knows it must be the lowercase a from the uppercase A type, right? So if I run this, all no problem. That's really, really nice. Okay, that's really just overloaded my duplicate record fields. Now, the next thing is overloaded labels. So this is a little bit magic. So what do we have here? This already is not standard Haskell, because what I see here is access of type symbol. So wait. Access is supposed to be a type, so I was wrong what I was just saying. Access of kind symbol. So what is kind symbol? Actually, we only have kind star in standard Haskell. So this already is an extension. Symbol is the kind of all values that... Oh wait. Okay. You can now use strings and mean types whose kind is simple. If you're confused, that's intentional. I'm just kidding. Let's look at an example. And you have a new syntax to use a hash in front of a label, and how this all fits together, I'll show you. So you can say, okay, the type true is an is label instance. Excuse me, this is another extension actually. You have multiple parameters to the type class, right? So the type class needs two parameters, the x and the a. Okay, now again. So the type true and the type bool make an is label instance, and the function from label returns the value true. We have this weird parameter that we ignore. It's of type proxy. This is another magic thing. So this is how you can work without having explicit type what's the right word here? I'm confused.
Annotations?
Not really annotation. So when you invoke it, you can't. I just said it previously. Anyway, I forgot. So you can't if you invoke a polymorphic function, the type application maybe, yeah. Even,
the explicit type application.
Thank you. Somebody paid attention. There was a test for you all. Thank you. Yes. Without this, you need these proxy types, and they really have no value. They're just here to force the type, the right type. So yeah, what does this feature give you? So you say, okay, the type true and bool, they form an is label, and the instance returns true. So now if you somewhere write the type true, and now you use this label syntax for that, it can be interpreted as a bool, and if so, the value is true. That's what this means. You can also say, okay, the type false and bool make an is label, and this time the value is false. And now the interesting thing is, you can also say, well, the type true and integer, they also form an is label, and this time the value is 1. So now if you write the label true, you need to tell the type system, so which t you're talking about. Do you want to interpret this as a bool or as an integer? And depending on this, it's going to be, which one is it? False or 1, right? No, excuse me, true or 1. And indeed, if you look at this program here, so I say print A is false, false is mapped to false, that's fine, I print it. And in the case of B, I need to tell you how I want to interpret it. So what does this give you overall? You can now map labels to arbitrary values, right? Okay, how is this useful? Well, there's one use case up in the horizon, and there might be more use cases in the future. It's not clear exactly what those could be. But the one we see already is the overloaded record fields. And this is the feature that is not in GHC yet. So you have two new type classes called Haskell and UpdateField. And overall, what you can do, or excuse me, I forgot to highlight this row. If you look at the type of getID, so we can have two types that have this the same record field name, this time person ID. And now I can write, oh listen, so I'm looking for an R, and all I know about this R is that it has an accessor, record accessor called person ID of type int. And if you give me that, I can return you the int. Right? So it's a little bit like row types, a little bit. But I'm not so strong in type systems, so I can't really tell you if this is the same or not. So anyway, so now you can use this funny little label syntax to say, well, I mean this accessor function, right? And this constraint you see, the type of getID, will be translated to has field, so that this type has at least the field person ID. So a lot of magic ongoing here, but that's the idea of it. And it gives you a little bit a sense of duck typing, right?
Structural typing.
So you go like, yeah, I don't care what this is, as long as I can ask him how it's called, or I can tell him how much it costs, I'm fine, right? Let's see where it gets us. It's interesting.
But unlike that typing, this is compile time type safe, right? So that's the
Yes, unlike duck typing, you actually have yes type check.
statically type check.
Yes.
Like, so that's great.
Yes.
Structural typing.
Yeah. Yeah, and if you run this program, well, with no surprise, we get the two IDs that we put into this, the values beforehand. Okay, next feature, stack traces. Finally, yay! Well, broken slide. Okay, so let's look at this example. The classic case for errors where you pull your hairs until you finally find it, or not. You just start all over again the project. So you want the first element of a list, and what if the list is empty? Well, I don't know what to do else, so I'm gonna throw an error here, right? And this is really terrible to find, because all you see is, you know, in one of your multiple threads, somewhere somebody tried to access an empty list, and I don't know how to deal with it. Screw you, right? That's basically what you get. And now debugging this is really, really hard, especially due to laziness, right? You should try it at some point. It's really enlightening. Like nothing. Like if you think like you can trace your way through it, no. You can be long past this code point, but the thing is not developed until way, way later, and only then it blows up. Could be a different thread, could be anywhere, right? It's really fun. So we want to know, okay, where did this come from, right? So we need something like stack traces. Now in a pure, and especially a lazy, purity is not the problem. In a lazy functional programming language, what is a stack trace is really not so easy to answer. It's not what you know from Java or C++. Think about tail recursion, for instance. If you do tail recursion, you reuse the same stack frame, so it's gonna be missing from your stack trace, which is one of the reasons why the Java community refuses to have tail call optimizations, because you would screw up their stack traces. They don't tell you anymore what exactly happened at runtime. It's gone, the frame is gone, right? So how is GHC solving this now? So let's look again at this example. So F is whatever, doing some stuff, looking at the head of the list, and if it's 0, it's 0, otherwise it's 1. And G is whatever, is doing some stuff, going over the list, and at some point call F, right? And if you run the program, it will actually blow up and tell you, well, the list is empty, head empty list. This error you just saw. So before GHC 8.0, you had some chance. You could recompile the whole thing with profiling, and then pass a flag called XC to the runtime, and then this time it will pay attention to what is happening, and it will give you a stack trace that looks like this. So this is already pretty neat, because now you see actually who called whom when the thing blew up. But the problem here is I really have to recompile with profiling, right? Okay. You can also compile with DESG, which gives you dwarf support like debugging symbols, and then run GDB. But it's not fun, I can tell you. I tried it a little bit. It's really, really confusing, because the whole laziness really is weird. Nothing happens when you expect it happens. So it's really hard to follow execution of a Haskell program in GDB. Okay. Now with GHC 8, there's a new feature called Haskell stack, and if you run the program, it will tell you this time. Well, it will tell you, at least I know who called the function head. So the caller, the one call side. You can also run it with prof again. You get both stack traces. It's fun. And you can NL profile and XG, and you get 3 different stack traces. So yeah, I guess at some point you're gonna have to clean it up and settle for one of them. So right now you have 3 ways to realize where you're at. Yes, go ahead.
Does it bring overhead stack trace?
With profiling certainly,
Yeah.
the Haskell stack has some overhead, yes, but it's controllable. Let's look at it. Okay, so how does this API look like? So there's a new type class called Haskell stack. It's a magic one. There's no instance of it really, but you can use it to tag your function and say, well, listen, for this function I really care who called me. So if somebody calls me, please take notes who this was, right, where it came from. And if the function that calls you also is tagged with Haskell stack, he will also add the stack frame to the stack, right? If he is not tagged, this will not happen, right? So the reason why previously like this output happens, because error now is tagged with a Haskell stack. That's why you see at least the final call side. Was this true? Yes, it's true. Yes, but still the function head will not do this. It will suppress the call stack to behave as before. Okay, so if in this example, just the way I showed you, the stack trace would look like this. So G called F, F called head, and that's where it blew up, right? If only F is tagged, excuse me, not head, I'm sorry. So F calls error directly in this case. So let's go back a step. So G calls F, F calls error. That's what happens here, right? In this example. And I can also show, no, wait a minute. No, that's fine. Okay. I'll get to this later. So, okay. So you see this full stack, the full stack trace. If only F is tagged, then G is missing. If only G is tagged, then F is missing. And G is missing. Right? And there's another feature. We were just talking about generalization, so they went the whole mile. So you can say, well, I want to freeze the call stack. From now on, no matter what the functions require, don't add any more stack frames. So this time, even if both F and G are tagged, only G will appear in the stack trace, not F. Why? I don't know, to be honest. So I read a little bit. Apparently they want to hide implementation details from libraries sometimes to not confuse people. Well, if you look at some standard Java stack traces, it might be actually a good idea to not show like all the 500 layers. But yeah, so it's not really like you really have, although it's called stack trace, it's not so much what you're used to from other languages. You really can, and this gets back to the overhead question, you can control the overhead, right? If you tag it, there's some overhead. If not, there's no overhead. But then you don't see the stack trace, right?
I think one idea why you want to provide this feature was also that people could provide their own stack traces to specific topics. Let's say you make some library or what, and inside it does a lot of network communication and so on, but you only really want to provide a stack trace that contains only the user-relevant functions. For example, every time something goes in and out, and the various function calls in between are not supposed to be in your library-specific stack trace. I think that's why they made it so that you can basically make more condensed stack traces for your specific case.
Interesting, thank you. Okay. So now you can also, at runtime, look at the stack trace itself. So there's a function called getCallStack, and if you just print it, this is what you get. So the printing is just done to show you what is in there, so there's no requirement for I/O to get the call stack, right? and it will give you the value of type source location will just tell you, okay, where you just came from, the caller site. Questions?
How heavily is Haskell implemented in standard library?
Excuse me?
How heavily is it used in standard library, this calling mechanism?
So in my understanding, and I must say most of this I just inferred by reading stuff up, right? So it might be not totally accurate what I'm saying here. In my understanding, the standard functions like head and so on, they maintain their old behavior. They will not show you a stack trace. Yes.
Is there any compile option to disable this? For example, if you want to achieve maximum performance, like to ignore all annotations, it's called stack.
I don't know. So the question is, can you disable this? I guess, I'm not sure. I could imagine the main function could be called with frozen call stack. I could imagine if you do this at the top level, that this might have an effect on the runtime, but I don't know.
Actually, I think in the library, I think at least for the feature that was added before this one. So before there was a similar feature that was implemented not with this constraint, but with like call stacks via implicit parameters that are like a similar but more exotic feature. And for that one, it was that we implemented it only for like undefined and error. So like in the standard library, so that only you would feel the performance impact only for functions that terminate your program anyway. So as soon as you go into error, undefined, it's over, right? So and thus for like higher level code, you as the programmer could choose whether there is like the Haskell stack equivalent or not. And then you could add it only to those where you know, that leads to something that will eventually be bad anyway. And thus you wouldn't suffer the performance. But I wanted to ask, do you happen to know what will happen to the implicit parameters feature that like was done before this one? Will it be replaced or will it still work?
So it uses implicit parameters to implement it.
Okay.
But this is supposed to be an implementation detail you should not rely on.
No, because it was publicly exposed for 7.10.2, right? So I was just wondering whether it means that we can still use that for some time, or whether with 8.0 it will stop working.
So implicit parameters are still in the language. They didn't remove them. But the call stack support uses them, but it's supposed to be implementation details. Right. So implicit parameters for everybody else. So you can say, well, you know, if somebody calls me, I expect a parameter of this type, but anything that is in his scope at this point, I'll take that fits the type, right? Scala has a similar feature with implicits and stuff, but it's not very much used. It's very exotic, and some people argue it should go out of the language, but now the call stack stuff is implemented with this, right? Because somewhere you need this value where you can attach the frame, the stack frame. So there must be some value behind the scenes being passed along, right?
And this is one of those typical double-edged swords. Like it can be really helpful to reducing complexity, but it can also introduce a lot of obscurity. Because like if you have 50 implicits, then you don't know what's going on. So it's really kind of.
Yeah,
Scala makes heavy use of those, but you really need to be careful what you import.
It has to be better though, because you always have to name them.
Yeah,
it doesn't pull them.
But even in good Scala programs will tell you, like, you know, please don't use them much, right? Don't overuse them. So,
and another question is, so with the implicit parameters, you could have multiple call stacks on the same function. So you could have like one call stack that is like the standard one, just called lock, for example, or what, that just goes through. And you could have another IP also of type call stack that would just contain, let's say, the one for your libraries. And I'm wondering whether with this thing, can you still have multiple parallel call stacks on one function?
I don't think so.
Or did they reduce it to one?
I don't know, but I haven't seen anything like this.
Yeah.
I don't think so.
Okay.
So I guess what you have to do is like collect the bigger set and then filter later.
Yes. Because, or the other, I think one way you could do it is if with this frozen call stack you get the G out, right? and or let's say you get the no, it only suspends it, right? It doesn't give you an actual handle on the call.
No, with frozen
Right.
call stack, it's really like semantic-wise, it doesn't change anything on the rest of the program, right?
Yes. Okay.
Other than the
Makes
call
sense.
stack behavior. Okay. Good. The next, in my opinion, really big feature is strict Haskell. So, Haskell is lazy. This is great. It's also terrible, depending on which situation you are and who you are. And anyway, so, and the big debate is what is the better default, right? I think by now it's clear that a really, really modern language, a good language, needs to support both, because sometimes you really want to be lazy, and sometimes you really don't. And Scala, if I may say this again, has features for laziness, and you need special syntax and say, okay, this time don't evaluate until I ask for it. So in Haskell, the default is lazy, which is really, really nice because you can, write stuff down in a mathematical manner. Laziness gives you a very high degree of decoupling of things. If you want to be blown away, look at strategies, for example, for parallel computation. So you have the algorithm in one module and the information how to execute it on a multi-core machine, a completely separate code base. Wow, how is this possible? Well, laziness is your friend here, right? Okay, it's really great to have it. But sometimes it's terrible for performance, right? The infamous space leaks. It's not really a leak like in Java or C++, where you just really forgot it and it's going to stay there forever. The memory will go away at some point. You will consume the thunks. Most likely, actually. The problem is that the memory peak, right, that it involves. So I'll give you an example for this. Okay. All right. First of all, introduce the feature. So in Haskell, you might find data type declarations. You might find function definitions, let expressions, cases, and so on. And if you enable strict, then basically what it does is add a bang everywhere where you can. If you just want to do this for data types, there's a subset of the strict features called strict data, which does it only for data types. And the bangs force the values. Every time you pass in a value, it will force the evaluation to be kept normal form. I need to say a couple of words regarding the case. So cases are actually already strict. But there are two interesting corner cases. So if you look at case x of y is just a variable. So what this is doing, it is forcing x itself. So this is another way of forcing the evaluation of x itself. And the other one is if you have new type wrappers, it will force them as well. Okay. So why does it matter? So let's try to measure a difference, okay? So a little bit silly example, I admit, but at the same time it's a simple example. So I have a data type that just wraps an int. I have a function that can add two of those thingies by extracting the ints, adding them up, and wrapping them up again. And I have fold R. The reason why I use my own fold R, not the one from the standard library, because the standard library is pretty smart. It uses fusion, and the whole effect goes away anyway. So with this one, it won't happen. Okay, so I do. This is actually a standard fold R, and I create a rather longish list, and I add everything up. Okay, so that's what I'm doing. Now, if you look at this, and so the accumulator, the value of type B, it's actually just a single D with a single int in it, and every time I add the next one on top, I could do the summing immediately and only need a single D in memory all the time. But laziness doesn't do this. Laziness just goes, yeah, I'll do that later. Just remember, if you need it, I will do it, right? So you build up a whole bubble of, later I'm gonna add those Ds, and those then actually are later put in there, and later I'll put them in there, and so on and so forth. So I don't know how many, this is 10 million to 100 millions layers of laziness you just build up, and only at the very end, where the print actually calls show, and then the show says, well, what is the integer? Please tell me. Oh, wait a minute, I need to do the calculation now, right? And then it goes and... another interesting case I want to say where laziness really can bite you if you work multi-threaded. So you think you're smart, you have like some computation that is expensive, you fork off a thread, you tell, okay, do your thing, and put it back into the M bar, and the thread goes, done, and when you touch it, then you pay for it, right? So, okay, this is not so trivial. So there are good reasons why sometimes you really want to be strict. Okay. So now if we benchmark this, so we compile with optimization on, and then we use the Unix command time to just have a quick look at how long things take. The non-strict version takes 3.9 seconds, and the strict one, wow, 0.15. So that's a big difference, right? How much is it? Like 100, what is it? Factor 10, factor 20, whatever. So that's a big difference. Okay, so why? What is happening here? Okay, let's look at the memory usage. So if we compile with profiling and then enable -t in the, it will dump me memory statistics. So the non-strict version uses what? 3 GB of memory. Okay, and it does like 9,000 garbage collection cycles because at some point you need to clean up, right? While the strict version uses only 1 megabyte of memory, right? So there you go, right? If you look at the core now, at the GHC core, to understand better what's going on, why this is happening. So this is a non-strict version of fold R. Well, it's basically what you expect, right? You case on the value on the list you're supposed to traverse. If it's empty, you return the accumulator. Otherwise, you call the function and it recurs, right? The strict version does this funny thing, and I just told you what happens if you case on a variable. You just force the value, right? So this is how f and d. Actually, he even forces f every single time because who knows, right? But I guess the optimizer will throw this away later. So yeah, here you go. So this is where the values are forced and the thumbs are thrown away immediately. And with some more optimization, if you use new type wrappers instead of a data type, and so on, the whole thing will actually boil down to a loop, because that's all you do, right? That's pretty neat. Okay, so this brings me to the end of my presentation. I forgot the obvious thank you slide, but anyway, I thank you for your attention. If you have any questions, please ask me. All right, then happy coding. See ya.